How is everybody doing today? I hope classes are going well. You're getting in the groove of this online school thing. Today we are going to look at 2.4. 2.4 is the product and quotient rule. So if you remember back in 2.2, we learned some of the basic rules for taking the derivative so that we can take the derivative of almost any polynomial we're given, okay? So we're good to go with our basic rules, but what's gonna happen now is we're gonna see some uglier equations, and we need to take the derivative of some uglier equations. So specifically, if we have a product, so if we have multiplication going on, or if we have division going on. So we have two rules there. We'll start with the product rule. Just make a pen that works nicely. And then we'll move on to the quotient rule in a little bit. So the product rule says that if you want the derivative of two functions that are multiplied together, so you're asked to find the derivative of f of x times g of x. Now, the problem with this is that it doesn't work the way you want it to. You don't just go through and take the derivative of each one separately. Okay, we've got to go through this, has a formula to it. So the way we do this is we start by taking the derivative of the first guy times the original second guy, plus leave the original first guy times the derivative of the second guy. So that's what we get. So derivative of the first, leave the second. Leave the first, derivative of the second. Which means that when you're using the product rule, your answer is almost always going to be uglier than the original question because it's going to have addition and multiplication and all sorts of stuff in it. So let me give you an example of what we're looking at here. So let's say that we had y equals 3x minus 2x squared times 5 plus 4x. If we want to use the product rule here to find the derivative of this guy, using what we've got up here, we've got two pieces multiplied together. This says that we should take the derivative of this guy. So we take the derivative of this guy, we get 3 minus, bring down that 2, 4x. Leave the second guy. So we leave that second guy alone. Then it says we leave the first guy, so we leave 3x minus 2x squared, and we find the derivative of the second guy. So the derivative of the second guy, the 5 is going to go away, the derivative of the second guy is just going to be 4. Does everybody agree? So if we simplify, I suppose we could do some FOIL here, but at least we can simplify this back part because it's a little bit easier. We could say 12x minus 8x squared. And yeah, I suppose you could FOIL that out and simplify it all the way down. But do you see what I'm talking about how it doesn't really get simpler? Now, something that some of you might notice here is if we have to FOIL to simplify, why didn't we just FOIL at the beginning? So with this product rule, we could have just FOILed at the beginning and not had to worry about the product rule at all. So FOIL first, and this is easier. So what this is telling us is that just because we have this rule doesn't mean we always have to use the rule. So in this case, if this was a problem that I was given, I never would do this here. The first thing I would do is FOIL that out, and then I would find the derivative of whatever I got when I FOILed it out. But the point was to practice this, so that's why we're doing it, okay? So we practiced it. So let me give you another one here. I'll stick it right here. So let's say we had f of x equals 1 over x plus 1 over x minus 1. So on this one, the idea is you still could FOIL it. It's not horrible, but we're getting into things that are not quite as nice anymore. So if we want to use the product rule here because it doesn't look as nice, that might be the thing. Now remember that we never want to leave something like this. So the first thing we're going to do is just write that as x to the negative 1 plus 1 times x minus 1. Now, if we want the derivative of the whole thing, it says take the derivative of this guy first. So the derivative of this guy, we bring down the negative 1 and then lower the exponent, so that's going to be x to the negative 2. And that guy goes away, right? And then we multiply it by the second guy. Plus, we leave the first guy, x minus 1 plus x to the minus 1 plus 1, and we take the derivative of the second guy. Now the derivative of the second guy is just the derivative of x, which is just 1. So what we end up with here, if we want to simplify a little bit, is we have this negative sign, and then we have this x minus 1 up top, but can we put those x squareds down on the bottom? Don't forget this minus sign is still out here. And then here, that doesn't change it at all, does it, that 1? So we have plus 1 over x plus 1. So you see what I mean about how it started out like this, and it certainly doesn't get any prettier looking once you take the derivative. We took the derivative of the first, leave the second, then leave the first, derivative of the second. Let me give you one more. Let's say g of x was equal to 2x times 3x plus 7. Now, if I was going to ask you to find the derivative of this guy, the question is, if this was on you, not on me, what would you do? Now, I do see a product, but is that the rule you would jump into? Okay. Or would you maybe do something else first? So could we rewrite this guy right off the bat as 6x squared plus 14x? Now, if we rewrite it real quickly here, if it's in this form, what's the derivative? So do we end up with 12x plus 14? And so by doing the distribution up front, it made our derivative really easy. But I also want to show you using the product rule. I want you to see that both forms work. So if we were using the product rule here, hopefully we're going to get the same answer. It says take the derivative of the first, leave the second. So the derivative of 2x is just 2, leave the second. Plus, leave the first, 2x, times the derivative of the second. Now the derivative of the second is just going to be the 3, isn't it? Okay, now we have some distribution that we can do. So we have 6x plus 14 plus 6x over here as well, which when we put this all together equals 12x plus 14. And lo and behold, that's the same thing it equaled over there. Phew, okay. So this example was just to show you that using the product rule should always work, but distribution here worked just as well, if not easier, because it was a couple fewer steps. So it's just what you like better. If something is easier to distribute or FOIL it out, rather than doing this. Now, this means that the product rule ends up being most people's least favorite. Of all the rules we're going to do, the product rule is most people's least favorite. But the problem is that there are going to be times when we have to use it. And when we have to use it, you need to remember it. So even though you might not use it very often because you're like, what the heck, I'm just going to multiply that out and then do it easy. There are some times when it's a necessity. So even though you might be like, no, I don't want to do this, practice the product rule just so that you get it in the groove, so that when we do need it, you're not like, oh God, I don't even remember how to do that. Okay, so you want to practice that product rule. Now, the rule that we definitely do need, there's no way of getting around it, is the quotient rule. Doesn't matter whether you like it or not, you got to use it. So let's look at the quotient rule. Give myself enough space here. So let's say that we wanted to find the derivative of f of x divided by g of x. So if we have two functions that are in a rational function, so we've got two functions that are divided by each other, and we want this derivative. Now again, unfortunately, it doesn't work nice. You don't just take the derivative of the top and take the derivative of the bottom. We've got to do something special here. So this is how this works. We start by taking g of x times the derivative of f of x minus f of x times the derivative of g of x. And then we divide the whole entire thing by g of x squared. So not super pretty. But as I said, there's no way of getting around using this rule, the quotient rule, so we've got to use it. So even though it's uglier than the product rule, most of you guys will just get in the habit of using the quotient rule, even though it is worse. Now, for most calculus students, there is a little rhyme that goes along with this. If you think about this as high and low, okay, so the high function and the low function, the way most people remember this is low d high minus high d low over low squared, and away we go. And I'll tell you, after almost 30 years, 28 years that I've been doing calculus, 28 years, yeah. After 28 years, when I see a quotient and I have to use the quotient rule, the first thing that pops into my head is low d high minus high d low. Low d high minus high d low. Because I have to remember, because of the subtraction, which one comes first and which one comes second. If you do them out of order, you get it wrong. So low d high minus high d low. So let's look at that then. So if f of x is equal to x minus 1 over 2x minus 3, they ask us to find the tangent line when x equals 1. Find the tangent line when x equals 1. All right, well, they've given us a function, and then they ask us about the tangent line. So we have to fall back on what we've learned so far. As soon as something says tangent line, we need to think derivative, right? Tangent line, derivative, tangent line, derivative. So it's asking us to find the derivative of this function to start with. Then later we're going to do something with that. But to start with, we need to find the derivative here. Okie dokie. So we're going to use our little rhyme over there, low d high. So we start by taking the low guy, 2x minus 3, times the derivative of the high, which luckily is just 1. I'm going to write it in here just so you can see it, but you don't really even need to write it, do you? Okay, but at least so that you see it. So low d high minus high d low, so the derivative of the low is just 2. And then we're going to put that all over 2x minus 3 squared. Now, here's how this works. When you do the quotient rule and you find this derivative, the bottom, don't ever worry about foiling it out. You don't have to mess with that at all. But you must always simplify the top. Never, ever, ever leave that looking like that, okay? So we will simplify the top. Just make sure, we distribute in that 2 to each one of those. So we'll have negative 2x and then plus 2, right? The two negatives will make a plus 2. All right, so then when we simplify, we're gonna have 2x minus 2x. So those two guys are gonna go away. Boop, boop. And then we'll have minus 3 plus 2. So minus 3 plus 2 is gonna give us a negative 1 over 2x minus 3 squared. So a lot of times, the top is going to simplify. Not always, but a lot of times, into something nice. The bottom is always going to be squared. Just leave it. But the top will simplify. So if we can simplify, let's go for it. Okay, so we got our derivative here. This is our derivative, but we're not done with the problem, are we? Because the problem asks us to find the tangent line when x equals 1. Now, if we remember that our derivative means slope, if we plug in 1 here, we should get the slope, shouldn't we? So we'll plug in 1 for x. Don't forget to square it. So we'll have negative 1 over, so let's see, we end up with 2 minus 3, which is negative 1, squared, which is positive 1. Oh, how nice. Oh, positive 1. So our slope just ends up being negative 1. So we know that we've got an x value of 1, we have a slope of 1, but if we want a tangent line, don't we also need a y value? What a pain in the butt. They didn't give us the y value. So in order to get the y value, if you know the original x, could you go back to the original formula and plug it in to figure out what the y equals? Right. So that's unfortunately what we have to do. So y equals, we'll plug it in up there, 1 minus 1 over 2 times 1 minus 3. Oh, look what happens. The top equals 0, the bottom equals negative 1, but the top being 0 means it's going to be 0. So we know that our slope is negative 1, and now we know that our point is the point 1, 0. So we need to find the equation of our line. So we're going to go y minus y sub 1, well our y sub 1 was 0, equals m, negative 1, times x minus x sub 1. So that will go away and just leave us y, which is nice. And this is going to be minus x plus 1. So here was the derivative over here. So we finished with the quotient rule right here. The rest of this was finding the slope and the point so that we could find the equation of the tangent line. Okay, but we did it. So that was like about as long as it would possibly be. Okay, you found the derivative, the slope, the point, and the tangent line. We found a lot of information there. But we did it. We were able to do it. So let's look at another quotient rule. Sorry about that. You can push pause and write this down if you need to. So this time we're just going to find the derivative, none of the extra work. So let's say that f of x was 2x squared minus 4x plus 3 over 2 minus 3x, and we just want to find f prime of x. So a little bit uglier than the last one. If we want f prime of x, now I know I erased it over there, so you got to get that little mantra in your head, low d high. Low d high minus high d low. Low d high. So low means we're going to start with this guy, 2 minus 3x, and then the derivative of the top guy. So the derivative of the top guy is going to be 4x minus 4. Does that look good? Minus, so low d high minus high, this whole guy, 2x squared minus 4x plus 3. D low. The derivative of the low, be careful, is negative 3, isn't it? On that x, that's a negative 3. And then the bottom will just be 2 minus 3x. And don't forget to square it. So the biggest problem that happens when doing the quotient rule is people get so excited about the low d high minus high d low that they forget the denominator altogether. So try not to forget that guy. Now, as I said, the worst part about this is that you got to actually simplify the top of this fraction. Never would that be okay. Which means there's quite a bit of work here to do. So we have to FOIL this guy out. So we'll have 8x minus 8 minus 12x squared minus 12x. This minus and that minus will change it into a plus, which is really nice. So then we'll just have plus 6x squared minus 12x plus 9. 2 minus 3x squared. Okay, so some FOIL and some distribution, and now let's see what we've got here. So we've got 8x minus 12x minus 12x. So minus 24x plus 8x would be negative 16x. So negative 16x, that's those guys. And then we have the negative 9, or negative 8 plus 9 will give us plus 1. That's gone. And then finally, we're going to have minus 12 plus 6. So we'll have minus 6x squared. And I know some of you might look at that and go, ugh, it's out of order. But you know what? I'm lazy. They just said simplify it. We simplified it. I'm not going to put it back in any particular order. It's good. It's ugly, but it's good. All right. Did I do that right, or did I make a mistake? Hold on. So minus 24x, minus 24x plus 8x is minus 16x, right? Okay. All right. Just a couple more here. Just wanted you to see some kind of really weird looking ones. Okay, so this is the next one. G of x equals 3 minus 1 over x all over x plus 5. So this time, what we have is a complex fraction because we've got a fraction inside the fraction. And certainly you could change that to an x to the negative 1 and go through the whole problem and do it, but there's an easier way to do this to keep all of your exponents positive and all the numbers positive, and that makes the low d high and everything better. So the best way to go about this is a little trick. If we multiply the top by x, then we have to multiply the bottom by x as well, don't we? Okay. But we can do that. We can multiply the top and the bottom by x. So that's what we're going to do, and we're going to distribute in an x. And the reason why I chose x is because the denominator of this fraction is x. If this had been an x squared, then I would have chosen x squared over x squared. So whatever this ugly denominator is, it's not even that ugly, but that's the ugly part. That's what you're going to multiply by. Because look what happens when we distribute in. The x is going to come in, distribute to the 3, so we get 3x. Not horrible. But when the x comes in and distributes here, they're going to cancel, aren't they? And leave us just minus 1. Then on the bottom, the x is going to distribute in, and it's going to give us x squared plus 5x. So by multiplying through by the denominator, okay, of that little fraction, we have eliminated the complex fraction. And the nice thing is that we haven't made the what's left over too much uglier. It's a little bit uglier with this x squared in the denominator, but it's not horrible. Okay, it's still very usable. And we don't have any negative exponents. We don't have any 1 over x's going on there. So use that as a little helpful hint if you need. Now, if we want to find our derivative, we're good to go. So again, we start our mantra, low d high. So x squared plus 5x d high is just times 3. Minus high d low. High, 3x minus 1, d low. Bring the 2 down, so 2x, and then plus 5 on the end there. And then the bottom guy, all squared. And remember, don't worry about foiling out that bottom guy ever, just leave it. Top, yep, we got to work on the top. Okay, so let's see. Distribute in the 3, we have 3x squared plus 15x. And then minus, and then we got to FOIL this whole monster out. So let's see, that's going to put us at 6x squared up front. We're going to have 15x minus 2x. So we'll have 13x. And then at the end here, we'll have minus 5. All over this guy squared. Okay, so let's see what we've got here. Now don't forget this minus sign here. So 3x minus 6x is going to make a minus, or sorry, 6x squared is going to make a minus 3x squared. And then the 15x minus 13x will give us 2x. And then the minus minus will give us a plus 5. All over x squared plus 5x squared. Right? So when you do the simplification, normally the numerator, as I said before, normally the numerator will simplify. It's not going to be super pretty always, but at least it simplifies a little bit. So you see why you want to do this rather than leave it like that. That, who knows what that is. This is at least something that you could work with if you needed to, okay? So yes, we have to simplify here. All right, one more question, and then we would be done with this example. So our last question that we're going to look at is another word problem. And the thing with this word problem is, again, we're in business calc, and I promise we'll do plenty of business calc examples, but I want you to see where calculus gets used in other areas. So in other areas like the medical field, different sciences, we've seen velocity, so velocity deals with physics, but in the medical field or in the biological field, they use statistics too, but they use calculus as well. So this example is a biology example, a medical example using calculus. So this says, as blood pumps, I don't think this pen's gonna work very long, through, no, tried to give it a try, but I think it's done. All right, let me see. So as blood pumps through the body, your systolic pressure continuously drops. Suppose this is modeled by, got a lot of pens that are dying on me today. Should have stuck with my brown one. I was trying to give these guys this is going to be the rainbow lecture. So this is modeled by P equals 25t squared plus 125 all over t squared plus 1, where t is between 0 and 10 in seconds. At what rate is the blood pressure changing seconds after leaving the heart? So while this is an example that maybe none of us understand, I mean, like, I have a very basic understanding of it, it's an example that all of us have seen because pretty much everybody has had their blood pressure taken. So this is the idea behind testing blood pressure, having your blood pressure taken. So the idea is, as the blood leaves your heart, the pressure behind it follows this formula. And it's continually dropping as it leaves your heart. So the pressure is really strong as it leaves, and then as it goes through your body, all the way through your body, the pressure drops. And apparently it takes 10 seconds to pump the blood through your whole body. I didn't know that, I'm just going by what the formula says. So we've got the formula, and it says that the time can be between 0 and 10 seconds. And then it says, at what rate is the blood pressure changing 5 seconds after leaving your body? After leaving your body. It's not leaving your body. After leaving your heart, I don't know how far that means. Is it down here, like in your calf? I have no idea. But we can figure this out because rate of change means derivative. So just because it's not a example that we are familiar with, you guys in the business sense and me in the mathematical sense, this is not a problem that really either one of us would ever do. It's still something we can do because we know calculus. So we need to find the derivative of the pressure. That's going to give us rate of change. So derivative of the pressure. But unfortunately, we've got the quotient rule going on there, don't we? So that's what we're practicing here. All right, so P prime. All right, one more time. Low D high. Low D high. So derivative of the high, bring down the 2, will just be 50t. So low D high minus high, 25t squared plus 125. D low is 2t. All over t squared plus 1 squared. So, as we've seen in the other examples, let's go ahead and do some simplifying there. So here we're going to have 50t cubed plus 50t minus 50t cubed, right? Distribute that in, minus 250t all over t squared plus 1 squared. Now, the nice thing about this is those 50t cubes go away, don't they? Boop, boop. So what we're actually left with is negative 200t over t squared plus 1 squared. So there's our derivative, and it's simplified a lot. It's actually better than the actual original function was, so we definitely got it down. Now we want to know what that derivative is, or the rate of change 5 seconds after leaving the heart. So we want t to equal 5. Well, we can plug in 5 here. Plug in 5 all over 5 squared plus 1 squared. Okay, so up top that gives us negative 1,000. On the bottom, I don't know, 26 squared, I should know that, I'm a mathematician, but 676. Okay, so negative 1,000 divided by 676 is negative 1.48. Okay. Now, the problem is we need to figure out how to solve or how to answer this question. So I know that it's going to be something per second because that's what we're looking at here. We're looking at seconds. So we need to know how we measure blood pressure. Let's see, did I put it in here? No, I didn't put in here, but I said, I Googled this, and apparently you measure blood pressure, so you know, like when you do the blood pressure cuff in millimeters of mercury. So we have to do a little bit of info searching, because this again is not what our interest is in. So we can say that the pressure is changing at negative 1.48 millimeters per second. Okay? Or you could write out the whole millimeters of mercury per second. But remember, the per second part is important. And remember, the negative on there implies that the pressure is going down, right? Like the diver going down, the pressure is going down. Well, isn't that what the problem said in the first place? So does it make sense that your answer is negative? It should be negative, shouldn't it? Because that's what the problem says. As you pump your blood, the pressure goes down. Now we understand, okay, when you take your blood pressure, they measure the first number is high, and then the second number is low. The reason for that is the first number is when it leaves your heart, the second number is as it pumps it through your body, and it's apparently dropping that whole time. So that's how we get blood pressure, and that's why there are two numbers. What was it when it left your heart? What was it when they measured it the second time? I don't even know when they measured it the second time. Okay. But we did it. Okay, so lots of different applications besides business, so it's just kind of important to be a well-rounded person. But definitely using the quotient rule, okay, you gotta get behind the quotient rule. Nobody gets away without using the quotient rule. Do practice the product rule, even if it might not be your favorite. Do practice it a couple times just to kind of get the flow going there. Okay, so get the flow on each one. All right, sounds good. Okie dokie. See you next time.